further, which is now going to be applicable for ink checking, doesn't matter it's CMYK or special color, also in packaging application, and understand how we can define color more precisely. So this is called colorimetry. So we looked at densitometry, now we look at colorimetry. When we use some device to capture color, to reproduce color, the color is reproduced within the capability of the device. English में problem है किसको? I mean, everybody okay ना? Okay, fine. So when we reproduce color, color is reproduced within the capability of the device. Okay? So what you produce within the capability of the device is called device dependent color. Color is reproduced within the capacity of the device. If you have a cheap mobile camera, and on the other end if you have the very expensive digital camera costing about 50 lakhs, the components used in two different cameras are different. In 50 lakhs cameras, the components will be expensive, more precise, highly technical. In cheap mobile camera, the components will be cheaper. Okay? So the color capturing is not the same in two cameras. So that kind of thing we call device dependent color. So digital cameras, or they are RGB cameras. We shoot with white light, which is separated into red, green, blue, and 3 signals are generated. It has sensors like this. Any digital camera, whether expensive or cheap, it has sensors like this. So expensive camera has high quality sensors. Okay. Color scanners. Color scanners, we call them RGB because light is separated into its basic color, red, green, blue. Color monitors. They also display the colors from red, green, blue, phosphor. So we call them RGB monitors. So cheap monitors will reproduce the colors within the capability of its components and its ingredients. Okay. The expensive monitors which they use in defense and all that will be very expensive. So the colors reproduced there are quite of a high quality. Then printing systems. So here you have desktop printer, you have photo printer, you have printing machine, you have digital printing machine. So each device will produce the colors within the limitation of its inks it is using, the paper is using, the capability of the system. So each system will produce colors differently. So all this we call device dependent color. What is seen by a normal human person with no color defect, we call that device independent color. The color that is perceived by a man with a normal color vision. Okay. Rest is all device dependent color. So CMY black. Okay. So this is device independent color, what is seen by normal color vision. Okay. So this we have seen. So I am going to forget some of this. This we have seen, that negative sensitivity. Now this diagram I will explain. What we saw earlier, negative color sensitivity, is like taking red color out from the base. That's what happens in the human eye. So it is like adding red color in the blue-green area because it's all positive system. Okay. Here you can see two lines. This I'll explain you why two lines. One is called 2 degree, one is called 10 degree, but that's something we'll see later. Spectrum. This is the peak sensitivity of red, green, blue cones, which is the highest peak. This mathematics you can forget. If you use densitometer to measure all these different colors, for some colors the densitometer may show the same value, though visually the color looks different. Okay, that is why densitometer is not useful when you want to measure many different colors like this. Therefore it is useful only for CMYK because it measures 1/3 of the spectrum. Okay, to measure all these various colors the way your eye sees it, you need a different instrument which can measure at the 3 peak points the same as the human cone. Then only you can measure the color the way your eye sees it. So that is called, instrument is called colorimeter. Color is based on what is called color temperature. Okay. Now all this background information is very important to measure your inks in the ink kitchen, to measure colors in packaging, to understand the viewing light and everything. Every color is indicated by what is called color temperature. So color temperature scale is measured in Kelvin. Kelvin scale starts at -273 degrees centigrade. So 0 degree Kelvin is equal to -273 degree centigrade. Okay? Or 0 degree centigrade is equal to 273 degree Kelvin. This is an extended centigrade scale. You may call that as a Kelvin scale. So this scale is okay. It's like if you take a black object which does not reflect any light, black metal piece does not reflect any light, and if you start applying heat, it gets heated up, the metal will get heated up. Okay, and the point will come when the temperature becomes so high that it will start giving out color. When the temperature becomes too high, it's like if you see a candle, the wick of the candle is black, but when it lights, after a while you see that black wick starts looking red, because the heat applied is so much that after a certain amount of heat it starts giving out color. Or if you see the blacksmith tongs, when it heats up, after some time it will start looking red. Yeah, or the gas burner at home. Okay, so when the temperature becomes so high that it starts giving out the color. So the color starts with red, and as you go on increasing the temperature, it will become orange, yellow, green, blue, and so on. Okay. So this color what you get, that particular color, it says the color temperature of this color is so and so because it is related to that black body. Okay. So if the temperature becomes over 1000, the black part will start looking reddish, and as you go on increasing the temperature, it goes towards blue. So the blue, as we have already seen, it's a shorter wavelength than the red in our spectrum. So it has high energy. Okay. So therefore, when you cook the food, you need a blue flame because you want to have high energy to cook the food. When you light a candle, it is yellowish because you don't need high energy, you need light. Okay. So the energy has to be low. So this is indicated by Kelvin degree. Okay, Kelvin degree temperature. So therefore, any tube light you buy or tungsten lamp you buy, they write the color temperature there. It doesn't mean it becomes that hot, but the light, color of the light coming from that particular tube or bulb is equal to black body when it is heated up to that temperature. So the spectrum given or the light color of the light given from that light, it is equal to, it is related to that. So that's why it says color temperature is so much. That means light coming out has that particular color. Okay. You take out any tube or any bulb, you will find there is a color temperature there, right? So there is a CIE body for illumination which started in 1931 and they standardized certain things. So they have standardized on certain illuminants, and these illuminants A, B and C, that's what they call, and also to resemble the daylight or sunlight, they have also suggested 4 different lights. Say D50, that is daylight 5000 degree Kelvin, D50, D55 5500 degree Kelvin, D65 6500 degree Kelvin, or D75 which is afternoon light when the sky is not cloudy. Okay, that is D75 7500 degree Kelvin. So these are the illuminants they have standardized for industrial use. So the lighting industry has based their lighting based on this recommendation. So if you take the fluorescent tube lights, there are 12 different tube lights called F1 to F12 for different application. Okay. Now this will not match the CIE recommended illuminant exactly because some of the material available is not, I mean they have to do more research into materials to match to those recommendation, but still it comes close. So there are 12 different tube lights for industrial use. These are like this: north light, artificial daylight, cool white, so and so. Okay, they are given that description. Then there are gas discharge lamps. You know, you find these sodium lamps or you find this mercury vapor. Low pressure, high pressure, and so on. Okay. Xenon lamp. So this is a different class of lighting, which are gas discharge lamps, which sometimes you find in malls outside or you find on the street. They have certain purpose. They are not for color matching, but they have certain purpose. For example, mercury vapor, mercury light you will use on your UV printing machine. At the end of the machine you will have UV lamp. Okay. Incandescent, this is electric bulb. So you can see it has light output like this. So you can see it has less output in the blue region, it has so much output in the green region, and it has high output in the red region. So again back to basic, more red plus green, okay, that makes it lamp looks yellowish. So if you hold it next to the tube light, it will look quite yellow, okay, because it has hardly any blue. So in printing industry, we use 5000 degree Kelvin light, which is more or less balanced in the blue, green, red region, more balanced light. And the recommended lighting for that is F8 xenon, okay, that gives roughly equal to 5000 degree Kelvin light, balance red, green, blue. In textile industry, in paint industry, the objects which you look from a long distance, and also in the sunlight, okay, 6500 degree Kelvin, which is a more bluish light than 5000 degree Kelvin. Okay, so there is more blue and less of red. Okay, F11, F7, F2, these three tube lights, they come together. So there are, for any color you need basically three things. Person with a normal color vision, you need a light source, because without light you cannot see light, can be any light, okay, and you need so the light source comes with different colors, so therefore you need a standard light source to judge the colors properly, which in printing is this D50. Then you need the printed sheet, okay, or printed color. So observer, a person observing it, light source, and the object, printed surface. These three will give you final color. Okay? Final red, green and blue, how much is coming, how much you are perceiving, it's a combination of these three factors. Alright? Any question? So that will give you the final color. So this we call visual stimuli. So here wavelength by wavelength of all the three parameters is multiplied to get final reception, final color. So if you take the instrument, in the instrument you have a light source, you are measuring printed surface, and you have the sensor in the instrument which is in place of the observer. So that three together will give you final color. So these sensitivities, total red, total green and total blue from these three is called XYZ. If you don't want to remember, you can forget that, but remember that it gives you the final color, final red, final blue, final green and so on. So this is a lot of mathematics, so you can forget if you don't want to consider this, but with this mathematics it is further computed what is the total red sensitivity, total green sensitivity, total blue sensitivity. So 380 to 780 nanometer, all the wavelengths together, and then spectral power distribution of the illuminant. What is the whole spectrum given out by the illuminant, whole spectrum viewed by the person, whole spectrum coming from the printed surface. Okay? So this is then put into further equation to get what we call color coordinates of red, green, blue, and then is plotted on the diagram. So because it is based on the human vision, all calculations, this represents the human vision, and on this, when colors are plotted, they are plotted the same way as your eye sees it. Okay? So here, from the previous mathematics, if you get x and y, say small x and small y, that color falls in the blue region. If you get large y and small x, it goes in the green region. If you get large x and somewhat medium y, it goes in the red region. So color can be denoted from its x, y, z values. It can tell you what kind of color it is. Okay? So it is based on human vision, so here, that is why it is called device independent system of color measurement. If you see this diagram, you go around the circle, go around the shape, there is a whole spectrum going from blue to red, going through all vector colors. Okay? If you come away from the center of this to any side, the colors becoming more stronger and stronger, more saturated. Okay? And if you take several layers of this and put them one over the other, on the top all colors become light, at the bottom they become dark. Okay? Because color is a three-dimensional system, you need this 2 dimension plus height. So it looks like this, looks like this. So here you go around a circle, the color will change as per spectrum color. You come away from the center, the color becomes stronger and stronger. And when you go to the top, all colors become light, at the bottom they become dark. Okay? So this is how the color is defined. Because of the 3 cones, you need 3 parameters. So this is the color terminology. Hue. When the color changes, we say hue has changed. Yellow, red, magenta, blue, and so on. When color loses its strength, it can lose its strength because it is mixed with white or mixed with black. So saturation goes down. Okay? Color loses its strength. And this was the central scale, which we call lightness. So there is a hue, saturation, lightness. In Photoshop, if you see, you will find these same terms. When you want to change the color, you change any of this value and the color will change. In 1976, the diagram was changed to this, which is called uniform color space. Because if you see this earlier diagram, when you look at the 2 colors in blue and say green region, and visually they appear, 2 blue appear to have same difference as the 2 green, but when you plot them on the diagram, on the earlier diagram, the distance in the green region was too much compared to the blue region. So this was made uniform color space. So you plot the colors the way you see them. So diagram is more proportional to your perception, to what you view. So this is called uniform color space diagram in 76. Then it was changed to this, which I think some of you are familiar with this. So here, now you remember what I told you, perceptual primaries, psychological primaries. red, green, blue and yellow. So because we see that yellow also as a primary, in this system we also take yellow as a primary. So yellow, blue, red and green, because color has to be plotted or measured the way you see it. Okay. So it is based on human vision, so it's based on perceptual primaries. So 4 colors: yellow, blue, red, green. We talked about the cones and the rods. Cones gives you color. So there is some mathematics involved here in our, when the signal goes from retina to the brain. And this mathematics, the cones, there is a lot of interaction in between. So many signals. So one signal that goes to the brain, if the answer to this equation is positive, then color you see is red. Brain interprets as the red color. If this equation gives negative value, the brain will interpret as green color. So red and green. So you, therefore red and green goes on the opposite side. You can never get a color which is reddish green. It's either red or yellow. Okay. For this equation, when the value is positive, the brain interprets as a yellow. Okay. And when value is negative, the brain interprets as a blue color. And the third equation, the signal, it produces various shades, because if you have to transmit 3 signals to the brain separately, shades of red, shades of blue, shades of green, the data is so much. So it's a fantastic mechanism that these two will give color signal, and the various shades of color will be produced by, we call this black and white signal. So this is called chrominance signal. Chrome is color. This is called chrominance, and then luminance. Luminance is just various shades. Okay. So chrominance signals and luminance signal. So when it goes to the brain, okay, it goes in this fashion. One luminous signal and then 2 chrominance signal. Okay, so that's how the brain will interpret. And the excellent example of this, now you will understand if you are confused. We have this picture. This is called chrominance signal. You can see there are only colors. And this is the black and white signal. So when these two are combined, this is the picture we get. So brain works in this fashion. Television signal also works in the same fashion. Sometimes if there is a problem in the program, you will find that suddenly you will get only this signal or only this signal. Most of the time you will see this combination. But if one of the signal goes out for a moment, you see either this or this. Okay. In printing industry, you know GCR, or nowadays people call it ink optimization. Gray component replacement. It's exactly the same. Yeah, we do the same thing. We reduce color and then black is increased. Okay. So it's all the same. Whether it happens in television, it happens in printing, we only call it by different terminology. Okay. So this is how so because of this, the television are able to transmit many channels, because the file size or the data size is kept small. If they have to transmit 3 signals, each one with all the shades, the data size will be too big, okay, and then transmission will be slow. You will not get so many channels, and so and so. So that's in GCR. Okay. So when somebody has defective green cone, which gives us this black and white signal, he will see unsharp images. Okay. I told you that on the graph there were 2 lines when we saw that peak sensitivity of the human cones. The color sensitive cones have maximum concentration in the center here, and if you see something at a short distance, the angle here is 2 degree in the pupil, okay. Therefore sometimes in printing we judge the colors closely, so we use 2 degree setting in the colorimeter. There is a setting 2 degree or 10 degree. Outside this area also there is the concentration of the cones goes down, and the area covered including that is called 10 degree, because the angle it makes here is 10 degree. So if you are measuring for textile paint, you set the colorimeter for 10 degree. There is a setting in the colorimeter. If you set it for printing, you set it for 2 degree, okay. So that's why there were 2 lines earlier. Okay, so if you hold your right hand like this, which is about half the meter, the size of the thumb is covered by 2 degree. Surrounding area large is covered by 10 degree. So this is 17 millimeter. This is a 10 degree will give you 88 millimeter at half a meter distance. Okay, so we come to this. The circle which I showed, perceptual primaries. So here in Photoshop also you will see LAB. We have to measure our inks in LAB, in packaging special color in LAB. Everything we must measure in LAB, whether it's gravure, flexo, digital, screen printing, offset, same principle. There is no difference. So all for all printing applications. So here horizontal line is called A. The center is 0. If you go to the left of the center, the value is minus. So that is green, okay, like I explained before. If the value is plus, it goes to the red. And the vertical line is B line. So you go away up from the center, the color becomes yellow, that is the B positive value. Below it becomes B minus, so it's a blue. So when now I have 2 colors here in this area. One is this color, one is this color, okay. So these 2 colors, this color has more positive LAB value, positive A value as compared to this color. This color A value is so much, this color A value is so much, and the B value of this color is less compared to this color. Okay. So LAB of this color is this LAB of this color is this, but both are in the yellowish red region, that is A plus B plus, because right of the center is A plus, top of the center is B plus. So both are in the A plus B plus region, yellowish red. Here two colors are in the yellowish green region, that is minus A plus B. So if your color has a value in LAB value, if A is minus and the B is plus, your color will fall in this area. Okay? You can see all the LAB values in Photoshop, or when you measure you will see it. You can play with it. If it's A plus B plus, any color, it will fall in this area. If the color value is minus A minus B, it falls in this area, greenish blue. And if it is in this area, then it falls in reddish blue area, which has A value plus and the B value minus. Okay? So if two colors have the same LAB, they will fall at the same point. Okay? So those various colors I showed earlier, you have to measure them in LAB to get, because LAB will tell you whether colors are close or not close. Okay? If you measure dot percentage, you don't know color, because same dot percentage will produce different result on different paper, say on newsprint or art paper. So color will look different. But if any two colors have the same LAB, they match. And then on the L scale, you have to see which color is lighter, which color is darker. Okay? So that is CIE system. Entire color management is based on this principle. Without this, you cannot do color management. There is another system exactly the same called LCH. It's like when you measure the distance, you can measure in inches or you can measure in centimeters. So you can measure the colors in LAB or LCH. But here now the difference is L is same as before, how light or dark color is. Further away you are from the center, the stronger is the color. Okay? Center is white, grey or black. Further away, here yellow is stronger. So each area, that color becomes stronger. And since this is a circle, this is 0 degree, 90 degree, 180 degree, 270 degree. Okay? So here, the angle that is made will denote what the color is. That is called U angle. So if the angle is so much, it is this color. If the angle is that much, it is that color. If it is that much, it is this color. Okay? So this is called LCH. Chroma and U. U is denoted by the angle. Okay? And lightness is same as before, how light or dark the color is. So when you see the color, if they have the same value, two colors, that means they will match. So it's up to your application or customers what is acceptability of the color difference. For some application, some customers, they are very fussy, they want very small tolerance. With some customer, the tolerance can be a little bit more. Okay? So in commercial printing, the tolerance can be more as compared to packaging printing. So with color difference, now we measure how far away the color are, two colors. On the A axis, how far they are away from each other on the B, how far they are away from on the L axis. Or in LCS system, in chroma, that is difference in two colors on the C axis or difference in U angle. Okay. So that gives us what is called total color difference, putting all the three factors together, LAB or LCH. So we get what is the total difference between the two color, and then this is what it is. Difference between these two colors on the A axis, B axis and the L axis. Okay? That is, so this diagonal is a total difference between the two colors. This is what it is. Okay? That we call delta E, that is the total color difference. So this is the rough indicator. Up to 0.2 not visible, 0.2 to 1 very small, 1 to 3 small, 3 to 6 medium, 6 difference is very large. So this is a size of the ellipse. That means within the ellipse, even if the color moves, it doesn't show any difference. So the tolerance is more when the colors it becomes stronger. In gray area, the tolerance is very little, practically no tolerance. That's why we always judge from the gray. The gray, if his gray is coming gray, then we know it's good, printing is good. Okay? In monitor, in printing, in color combination, that's why gray is very important. Any slight difference will immediately reflect in gray. As you go to saturated color, the tolerance is more. So there are different formulas. This one was basic formula in 1976 that was derived, okay, for LAB and LCH. Then there is improvement further. Unfortunately, printing industry, most people are still using this old formula. Then there was one came in 94. You can see the size of the ellipse is changed. Then there is CMC, which is perceptibility and acceptability. The lightness is has double the tolerance than color. So this actually works much better, this formula. CMC 2:1 it is called. And then in 2000 further formula came in. So if you have good meter, it will have all the 5 formulas and you have to select. So you must select 2 degree, you must select formula, you must select all these things. Otherwise you are not talking the same language as somebody else. So the buyer, the printer and everybody must have the same setting in the instrument. If it's not the same, you can forget, you will not do color match. This is in addition to all printing standardization, ink checking, paper checking, substrate, standardization of the process, everything must be done. So you get the instrument which can measure LAB, it will show you delta E. There are many instruments. So far okay? If now thing is going towards spectrophotometry, okay? If you measure just at 3 points, there may be still some difference. The color will match under one light but will not match under another light. That we call metamerism. Okay? Now, why this happens? Now we have two colors here. Colorimeter will measure at these 3 points, but we have the difference here where it is not being measured. So these two colors will match under one light but will not match under another light. It's called metamerism. So now we need to measure the color with spectrophotometer, that is measuring the color wavelength by wavelength throughout the spectrum to get, once you match color with this, it will match under any light. Okay? This spectral measurement of color. So you need good instruments, and this is what I use. I have in my office. Works as a densitometer, colorimeter, spectrophotometer, all in one. So this is on colorimetry. This is the fundamental for color management. Okay? This is confusing, but I am sure that if you apply your mind, things will become better. We don't have time for color management to use that, to show you, because I think we have to do it next time. But if you have any questions on what we have done today, you can ask. Colorimetry applies to substrate inspection, films, foils, inks, printing, ink kitchen, everything, lighting, everything is important. Any questions?
That you told that delta E, you gave some values of delta E. So in industry, what are the delta E values that are acceptable to the customers?
It depends on your customer. Suppose I am doing printing for garment industry. If I am doing for paint industry, that paint industry may be more fussy about the color match. Yeah? Whether I am doing something for children toys, I am doing something for collapsible tubes. So it depends on what your customer ultimately accepting. So you have to set your own standards.
There might be some standards given like 0.2 or 0.5.
No. You have your customer. You have to decide your standard according to what customer is going to accept. Yeah? And then you have to use the instrument with correct setting and everything correct. Okay? This principle also applies in product manufacturing. If somebody in automobile, when the cars are manufactured, the colors are measured this way on the car. So you have to see what is the tolerance there. That may be still closer tolerance than the other industry. Okay? So this applies to product as well as package and printing all. Any question? So these fundamentals are very, very important. Of course, we also do a lot of implementation of color management in the industry. So we are going with many companies. So when they want in-house implementation or program, then we actually go and work with them to set the standard. No question? Yes?
In case of lab values, now suppose I am having paper as my substrate, but if I have a virgin board or if I have a grey back board or a metallized board, will my lab values differ?
Yes, lab value, if you use the same ink, the lab value will differ. So you have to modify the ink to achieve the same LAB value.
And in case of...
So if you are printing on say board, and then you want to print something on the different substrate, say non-absorbent, you need to modify the ink use different ink, which will give you the same LAB as the board on that. So LAB will match, but the ink components will be different. Yeah. And of course, you have to take care of lighting and everything. Set the right lighting in the meter and so on. Yeah. Any other question? So color management and packaging. Actually, I have another presentation also, but we don't have time. Maybe we can do it next time. How to try and achieve color accuracy. No questions? No more questions?
Can we possibly cover this profiling part? Will it be possible in your next session?
Yeah, that's what the color management is. That's the color management is. Color management and also how to apply for special color and spot color and packaging application. Because it's too much in one session.
Sir, I got one more question. So it's like we have heard that measuring lab values on MET board is almost not recommended. Like they're saying that the lab values may be exact, but it's very difficult to measure.
You have to use a different instrument.
Yes.
You can measure LAB value, but there is one instrument which measures at when you have metallic substrate or metallic ink, you need the instrument which is called multi-angle instrument or the spherical instrument, which will throw the light from different direction. So whichever way you put your metal, it will give you the right value. If you use 45 degree or 0.45 on a metallic substrate, because of the grains there, the direction in which you keep it will give you different value, especially L value, because reflectance will be different. So if you are using both, then you need two instruments in the company. Yeah, one instrument will not work. You are doing commercial printing or packaging printing?
Packaging.
Okay. From which company you are?
Since packaging.
Oh, Parson. Where, Daman or Chapter? Or you are from head office? Okay. Yeah. So you have two instruments? Parson doesn't have two instruments?
That is why we asked you for the metallization.
Yeah, you need two different instruments. You should keep second instrument. I mean, for the size of your company.
After the seminar, we recommend that.
Okay, finish.
Yeah. Tell Ramesh that you have to use that. Yeah.
फर्स्ट चैप्टर में जो आपने ग्राफ दिखाया था 3 कलर का, उसमें रेड माइनस में आ रहा था, वो क्यों आ रहा था?
Sorry?
नेगेटिव में रेड ग्राफ आ रहा था.
He's talking about that transcendence graph wherein the ray goes into
Minus.
That's how the God has created us.
Zero means absence of light.
Sorry?
Zero means absence of light. Then
No, when you see it here, the red in the blue-green region, it goes negative value. It's like red taking out from the blue-green. Not in printing, not on television. That's why you don't get those perfect blue and green, not highly saturated, you don't get. You follow that shape, that happens only here. You got it? No. That's how the God has created our vision. We have to ask God.
भारत में मिला.
Yeah? No more questions? Okay. Right, and if you don't have any questions, then it's fine.
So फोटोग्राफिक फिल्म
Sorry?
के जो एक डायग्राम दिखाया था, उसमें फर्स्ट पर ब्लू इमेजन था, बीच में ग्रीन और रेड.
There is a blue sensitive layer, then green sensitive layer, then red sensitive layer.
हाँ, तो रेड सेंसिटिव लेयर बड़ा था ब्लू से।
रेड सेंसिटिव लेयर
जो इमेज दिखाया था ना, तो रेड रीजन ब्लू से रीजन से बड़ा था, तो वो रेड रीजन ब्लू रीजन पर अफेक्ट नहीं करेगा एक्सपोजिंग के टाइम।
no, because the top layer is sensitive only to blue light.
वो रेड लाइट में
Red light will not affect. Old days we used to get the films which will expose, you can expose only to blue light. Then we had another film called orthochromatic, you can expose to blue and green. Then we had another film called panchromatic, all three will affect there. But probably you have not seen that technology. Similar way, the emulsions are here. First one gets affected only by blue, second one by green and third one by red.
तो 3 कलर के लिए 3 फिल्म यूज करेंगे तो
Then in printing we do that, no? That's what we call it color separation, 3 separate films. In photography you can't use you want to see single photograph, no? You don't want to see 3 separate prints and imagine it as a color print. Isn't it? You want to see color effect.
Sir, in between you had told that changing the, if we use CM, why can if we change that, why CM cures, the ink consumption will be more, why is it so?
I will need longer explanation because of the color defects of the pigments. Yeah. So maybe next time we will talk about density, other things. So we can talk about the color reproduction maybe in the next time. Color management, color reproduction, color correction. This was all on basic color, densitometer and new, based on human vision how to use the CIE system. Okay, anything more? Okay. Yeah. Yes?
This opportunity to thank Professor Kiran Prayagi. Thank you, sir. And we are indeed privileged because he has also been associated with SIS from the day of inception, including our syllabus framing for color management and the courses of printing and packaging technology. So we are. It's a pleasure to have him here. In fact, in a lighter sense, he has shown us what capability God has given us to and how we can comprehend color with this comprehensive theoretical science behind colorimetry. At the same time, he has given ample examples of the applications that these have in the field of print, package, the television systems and all. So it's indeed a great pleasure, and not to forget, this is only the first of the 6 sessions that we're going to have with him. And as he said, next time we're going to have on color management. It would be at GIPT, the next session. The date would be informed soon, so you can be in touch. And we'll of course thank BMPA because we have continued to have us as one of the 2 venues for these C-Core Samjo program, and hope we continue this association for future years too. Thanks a lot for the audience. I think we had a good interactive session, including the students who had come here. And we hope that we turn out in larger numbers in the further sessions also, and take a good leaf out of so I would say a small drop out of the ocean that he is. So thank you very much. On behalf of SIS, I bid a goodbye until all of us meet back again. Thank you very much.